Welcome to Cybersecurity Workshops. Today, we're going to talk about file links. So we're continuing Matt Vogel's introduction to the command line interface, and we're getting towards the end of the second module, which is all about files and directories. And so we're getting into some of the slightly more arcane aspects of files and directories in the command line. You know, the earlier stuff was high-level overview. Here's how the file system works. Here's how you create files, deleting files, listing files, removing files. Got into permissions, zipping files and directories, which is important. How to find stuff, that's important. We're going to talk today about links, which are like shortcuts. So if you think of a similar thing in Windows, you can create shortcuts to other files on the file systems, and sometimes that can be very useful if I want to be able to get access to a file from multiple places in the file system without having to do a bunch of directory changes and such. I can use links to do that. So we're going to talk about links today, and then the last sort of short discussion on files and directories will be finding information about files. So we'll dive right in here. File links. So we're going to talk first about an inode. What an inode is, has to do with how links work, and it's some useful information about the file system. It's something that you don't necessarily need to know in order to use it, but it's good to know. And if you sort of continue your education about computer operating systems, then inodes will be a pretty important topic area later on. So we're going to understand what an inode is. We're going to talk about hard links in the Linux file system, and then soft links in the Linux file system. So first, we'll start with inodes. So each file and directory in the Linux file system has an inode. Inode has a number that refers to a file or directory in the file system. And the inode is a data structure in the operating system that stores some basic information about a file. And we'll look at what that is here in a minute. And the Linux operating system uses inodes to access files and directories. So here's all the things that an inode contains. And again, this is a data structure that contains information about a file. It has information about where the file exists on the hard drive. So when you try to access it, the operating system can find it and get the data out of it. Information about what type of a file it is, what the permissions are, the owner group, the size of the file, the last time the file was accessed, last time the file was changed, last time the file was modified, and if a file is deleted, when it was deleted. So that's all information contained in the inode. And there's an interesting bit of data that's not on this list that you may have sort of recognized already. That is that the file name or directory name is not part of the inode information. So with all that list of stuff related to the file that's contained in the inode, the name of the file is not in there. That's because a file can have multiple different names, and each one of those names is a link to the file, right? So here we say this is because the file name and directory name is just a link to an inode. The file name or directory name is associated with an inode in the directory. So the directory is a whole nother data structure that contains a relationship between file names and directory names and their associated inodes. So the inode is what points to the actual file. In the Linux file system, a directory is a file that lists the file names and inodes associated. So again, the directory is this data structure that contains the list of files and the inode numbers associated with each one of those files. And you can see this, so you can view the inodes associated with a file name or directory by using the ls command with the -i option. So let's take a look here. So I'm in my home directory. So if I do an ls, I get the standard stuff, right? Standard list of files. If I do ls-i, I see the inode numbers associated with each one of these files. And these are these sort of, the numbers increase as I over the life of the file system. So as I add files later in the life of the system, those are generally going to have higher inode numbers. Okay, so let's talk first about hard links. A hard link is the association of a file name or directory name to the inode. So hard link is association of a file name or directory name to an inode. And every file in the Linux file system has at least one hard link. So every file that when you list files in different ways in the file system, every file has at least one hard link. If a file has no hard links, then that's when the file is considered by the operating system to have been deleted. So that deleted time, that's part of the inode information. When the last hard link from a file ceases to exist because the file name is deleted, when that last hard link is gone, then the file is considered to be deleted, and that time date is going to be stored in the inode. But that file is going to be, it's now going to be ready to be overwritten by new files that are created in the file system, right? So it's not, that file is not going to live forever once it's deleted. Eventually it's going to get overwritten, and that inode is not going to be there anymore. And so the last hard link that goes away, that's deleted, is going to cause the file itself to be deleted, and that part of the hard drive can be overwritten. A file can have more than one hard link, so you can have multiple hard links. So if I have a file with 3 hard links, I delete 2 of the hard links, that file is still going to exist on the file system. That inode is still going to be available because there's still at least one hard link to it. When a file has more than one hard link, all the hard links are associated with the same inode. Yeah, so the hard links are really tied to the inode number. Hard links cannot be created for a directory. Okay. So when you use the LSDashL command, one of the columns shows the number of hard links each file and directory has. So if I say LS-L, I see a column here after the file permissions. This indicates the number of hard links. So each one of the directories has 2 hard links, you'll notice, or more. So this ida-free-70 has 11 hard links for some reason. Most of the files have a single hard link. So this thing is called output file. It's got 1 hard link. There's the file 1, file 2 that I created. So if I just create a file in directory by touching the file, so if I say touch file 3, for example, that's going to have a single hard link because I just created it. Nobody has had an opportunity to create another hard link to it. And if I delete file 3, then it'll have 0 hard links, and now that space on the hard drive can be overwritten. Okay, so it's the second column there. The ln command is used to create a hard link. So here's the syntax. ln, original file name, hard link file name. The original file name and new hard link file name both point to the same inode or file in the file system. So let's see that. So I just created this thing called file 3. File 3 has a single hard link. So now if I say ln file 3 link. Now if I do an LSDashL, now you'll see that file 3 is there and file 3 link is there. And they both have 2 hard links because it's pointing to the same inode. So if I were to say then ls-i file 3 star, remember the -i option shows me the inode numbers for the files, and here's file 3, here's file 3 link, and you'll notice the inode numbers are the same. And again, that's because they're the same file. So now I could delete file 3 if I wanted to, rm file 3, if I do that, file3 link is still there because that inode still has a name to it, name associated with it. And remember, the directory is just this data structure that associates file names and directory names with inode numbers. And so now if I was to say ls-i file3 star, there's that same inode number. There's that same inode number associated with that same, with file link, with file3 underscore link. Okay, so that's hard links. So once a hard link to a file has been created, either the original file name or the new hard link file name can be used to access the file, right? Because they're just pointers to they're just this association between file names and inode numbers. Even if the new hard link is moved to another directory in the file system, the new hard link will still reference the same inode or file. That should be pretty intuitive. And then if the original file name is deleted, the file will still exist with the new hard link file name. I just showed that, right? So these are some more facts about hard links. Okay, soft links. Let's talk about soft links. And these are more like the shortcuts that I mentioned earlier. A soft link is another kind of a link, and it's like a file shortcut. A soft link does not have the same inode as the original file. A soft link does not have the same inode as the original file. A soft link just points to the original file. If the original file is deleted, the soft link will no longer work. So if the original file is deleted, since the soft link does not have the same inode number, when the original file is deleted, then there's no hard links pointing to that inode, so that file is considered to be deleted. And here's another different thing about a soft link. Remember, a hard link cannot be made to a directory. A soft link can be made to a directory. So you can point a soft link to a directory, which is a convenient thing to be able to do. The ln-s command is used to create a soft link for a file or directory. And then here's the syntax. ln-s, original file name, soft link file name. The original file name and the new soft link file name, they do not point to the same inode, right? So here's an example. Softlink will now show the association to the original file when it's viewed with the LSDashL command using it looks like a little arrow, right? It's the dash greater than, looks like a little arrow. In Ubuntu Linux, the softlink will be light blue, and softlink will have an L in front of, this is a lowercase l, not a 1. Softlink will have a lowercase l in front of the permissions, which indicates a link. So here's an example of all that. Here's file 1, here's file 1 soft link, and so here he's done an ls-li, so that's going to do a long listing, and it's going to show the inode numbers for the files. You'll see that these two files don't have the same inode number, and the link has an L at the very beginning of the file permissions, and if you look at the file name, here's the file name, file 1-soft-link, and then there's this little arrow thing, and it's pointing to file 1. So so I can say ln-s file 1 soft link. Did something wrong there. Oh, I did an ls. I meant to do an ln-s file 1 soft link. I'm not even going to edit that out. So now I can do an ls-li, and here I see there's file 1, has an inode number, and then I have file 1 soft link. It's pointing to file 1. It has a different inode number. It's got an L at the beginning. Now, why would I ever create a soft link in the same folder? I probably wouldn't, right? Because the point is to make it a shortcut. And the shortcut's generally going to be in a different folder. But maybe I want to create a soft link to, remember I have this thing called my directory. So if I said ls my directory, and then inside there's another directory, and inside there are a couple of files. So these are files that are in another directory, and maybe I want to keep those files in that directory, but I happen to access them a lot from this directory because I have some manipulation I do to them with a script in this directory or whatever. And so I want to be able to access those files easily from this directory. So what I might do is I might create a soft link to those files. So I would say ln-s, and I could say my directory / another directory / file5, and then I could call that file5 link. And now if I do an ls-l of my current directory, I see that I have this thing called file5 link, and that is pointing to a file that's in current directory / my directory / another directory / file5. And so now if I want to see the contents of that file, I can cat file. I can treat it just like a file5 link, and I guess it's an empty file. So if I cat my directory, another directory, file5. Whoops, typed in wrong. Yeah, it's an empty file. So if I did an ls of that, my directory, another directory, file5. No, file5. Really, I wanted to do an ls-l. Wow, I'm trouble typing today. Yeah, so that's an empty file. So when I manipulate it, when I try to cat it, I don't get any output. But you see, I can access that file now using that shortcut, which is convenient. So here's another fact about soft links. If the original file associated with the soft link is deleted, the soft link will remain but be broken because it no longer refers to a file. And a soft link that's broken will be read. So right now, if I clear things, so I'm in my home directory. If I say LSDashL file5 link, I'm going to see here's this. Okay, it's file5 link, and here's the pointer to where it actually exists on the file system. If I were to delete that file, not the link but the file, so if I say rm my directory, another directory, file5, if I were to delete that file and then do that ls-l again, it's read. So file5-link points to a thing that isn't there anymore. So instead of that thing being that light blue color, it's red, indicating the fact that that file doesn't exist anymore. And I can also now I can delete my link too. Remove file5 link. And I can do an ls, and now it's gone. All right. So deleting links, both hard and soft links can be deleted using the rm command, like I just did. If a file only has one hard link is removed with the rm command, the file will no longer exist. Deleting a soft link breaks the association of the soft link with a file, but will not delete the file. Okay, so I think that should be clear by now. Okay, so I suggest that students go ahead and jump into the hands-on exercise associated with this lesson, and teachers are going to have to provide that document to the students. So thanks, and we'll see you next time.